Namaskar. Today I am going to give a talk on bridges. The content of the topic is introduction, classification of bridges, geology of the site, geological parameters, bridge problems, and finally the conclusions. A bridge is defined as a structure which provides a passage over a gap without closing the way beneath. Bridges are media for the roadways or railways or footpaths. It also be defined as a structure built over a river, a dry valley, lowland or any depressed part of the land to provide a link between the two opposite sides. The first cast iron bridge was constructed in 1776 across the Severn River in England. The longest second cable stayed bridge was constructed across the Ugly River, Calcutta in 1992, named after the Vidyasagar Setu. The total length of the bridge is 822.96 meters. The bridge is supported by total of 152 cables. The bridge provides a direct link with the national highways leading to Bombay, Madras, Haldia and etc. Eye level bridge, a bridge constructed much above the eye floodwater level. All the floodwater passes through its vents. Arch bridge. Arch bridges are constructed with abutments at each end. The weight of the bridge is thrust into these abutments. Beam bridges. The beam type of bridge is the simplest type of bridge. The beam bridge could be anything as simple as the flanks of wood to a complex structure. These are bridges without horizontal beams at each end. They are either supported by single beam or a span or with multiple beam or spans supported by intermediate piers. Tied arch bridges. Tied arch bridges differ in structure from typical arch bridges. These are constructed in such a way that the weight of the bridge is thrust into the abutments. The bottom chord structure restrains the tension by the end of the arc. These type of bridges are also called as bowstring arches. Cantilever bridges. These bridges are constructed using a cantilevers or horizontal beams supported by abutments at only one end. It has a pier of spans from opposite sides extend to the center of the bridge crosses. Submersible bridge. One of the submersible bridge, one which allows the floodwater to pass over the bridge during the floods. Such bridges are constructed expecting flood levels in the river system. Cable stayed bridges. These are similar to suspension bridge in structure except that they are held by cables. Causeway. A permanent submersible bridge which allows the floodwater to pass over it. Culvert. A small bridge constructed across a small streams and across roads with a linear pathway of less than 6 meters. Linear waterway. The linear waterway of a bridge is the length available in it between the extreme edges of a water surface at the highest flood. This can be level measured at right angles to the abutment face. Underbridge. A bridge constructed to enable a road to pass under another work. Overbridge. A bridge constructed to enable one form of land communication over another. Piers. These are the intermediate supports of a bridge. Superstructure may be solid or the open type. Abutments. These are end supports of superstructures. Bindra in 1979 classified the bridges taking into various factors into considerations. One he has taken into considerations that is material used for construction. Based on the materials used for construction, he has classified there are two types, one is masonry bridges and another is steel bridges. Second, purpose. The purpose of the bridge is again classified based on the purpose, that is adequate, footbridge, highway bridge and railway bridge. Based on the life, either you can call it is a temporary or a permanent. Depending upon the flood level, we can also call them it is submersible and non-submersible. The nature of superstructure actions he has classified as level bridge, suspension bridge and truss bridge. And fixed or movable, the classification is based on the fixed or the movable bridges. One is called a swinging, lift or bascule. Span length. So, the culverts less than 8 meters, we call them it is a culverts. If it is 8 to 30 meters, we call them it is minor bridges. If it is more than 30 meters, we call them it is major bridges. And if you have a longer span, it is about 120 meters, we call them it is a longer span bridges. In general, there are 4 major types of bridges are as follows. Arc bridges. In the arc type of bridge, weight is carried outward along the 2 paths curving towards the ground. Following are the different types of arc bridges: concrete arc bridges, trough arc bridges, bowstring arc bridges, burr arc truss bridges. Beam bridges. The beam bridge type is the simplest type of bridge. The beam bridge could be anything as simple as a flank of wood to a complex structure. It is made of 2 or more supports which hold a beam. Following are the different types of beam bridges. One is long beam bridge and another is short beam bridge. Third, suspension or cable stayed bridges. The deck, that is traffic way of a suspension bridge, is hung by cables which hang from towers. The cables transfer the weight to the towers which transfer the weight to the ground. Cable stayed bridges have towers, but cables from the towers go directly to the road deck instead of spanning from tower to the tower. Following are the different types of suspension and cable stayed bridges. One is cable stayed bridge, suspension bridge, self anchored suspension bridge, simple suspension bridge or rope bridges. The fourth one is cantilever. In the cantilever type of bridge, 2 beams support another beam, which is where the deck or traffic way is. The 2 beams must be anchored and this must be done well. The following are the different types of cantilever bridges. One is cantilever bridge, cantilever span cable stayed bridge and etc. Investigation for site selection for bridges are as follows. Technical feasibility. Before undertaking a detailed survey of a major bridge site, it is necessary to gather a techno-feasible information about the region. All details concerning the proposed bridge site should be collected, such as published reports of the area, discussions with experts, selection 2 or more alternative possible locations, then assessment of traffic density, then construction problems, then locations of other bridges and construction materials. Geological studies. Major bridges require a strong foundation on stable rocks. It is not always possible to locate all solid rock for a deep foundation. Regional geology influences the geological conditions of the region. The engineering geologist has to prepare a local geological map of the region based on the study of the exposure of rocks, ilex, excavation sites, etc. It is required to prepare a strike frequency diagram based on available structural features. This study clearly illustrates the major structures of the investigated regions. Such data can be interpreted while designing the foundation. Hydrogeological studies. Hydrogeological studies of the region exhibit the water table of piezometric conditions of the proposed area. It is required to assess the water table conditions of the area. In some instances, aquifer characteristics are to be determined by proper interpretation of hydrogeological conditions of the area. In deep foundations, the bridge piers may reach below the water table. In that case, the quality of the water must be analyzed. The civil engineer will design the foundation material based on the quality of the surface water. The fourth feasibility, that is test boring or geographical studies. Deep foundations for major bridges require a subsurface details of the proposed area. It is necessary to study the depth of the overburden at the foundation site. Test boring is required to know the subsurface lithological variations and extent and thickness of the rock formations, etc. Soil investigations has to be done in this stage. It is necessary to determine the particle size and distribution, compressibility and settlement test of the soil sample have to also be determined. Detailed geotechnical studies have to be carried out. It is necessary to collect core sampling at least of one borehole from each foundation piers areas. Collected core samples have to be tested in the laboratory for determination of various geomechanical properties. Sometimes, depending upon the field conditions, geophysical survey have to be conducted to ascertain the subsurface conditions of the proposed area. Hydrometeorological studies. The civil engineer will study all available statistical and meteorological data of the proposed area. The civil engineer and engineering geologist will analyze the data for estimating maximum flood levels, characteristics of the river system, base level, etc. The civil engineer will design the height of the structures based on the river water data, etc. Foundation designs. While the site selected for a bridge is based on all the above studies, the foundation design completely depends on engineering skill. Foundation type and designs are the important components in bridge construction. There are number of bridge designs. All types exert a vertical load on the foundations. Finally, the seismic factors, that is earthquake resistance of bridges. During earthquake, many bridges suffer damages commensurate with the magnitude of the earthquake cause a slight damage to the bridges. Low magnitude earthquakes cause slight damage to bridges, whereas high magnitude earthquakes cause damage to the foundation, settlement or destruction of the bridge piers made of brick or plain concrete. Damage to foundation settlement arises from various unresolved natural problems. Damage to construction material is mainly due to brittleness of the material. Recently, strong piers material such as reinforced concrete or steel has to be used to reduce the brittleness of construction materials. The seismic zoning map of India reveals the seismic factors of each zone. In highly seismic areas, it is necessary to design the foundation based on the modified seismic coefficient methods. Selection of a suitable site for major bridges is dependent on all the above considerations. The considerations and maintenance of bridges also play an important role. In most cases, the location of bridge is decided more by socio-economic factors than by geological considerations. For example, there are 7 bridges over the river Jhelum connecting the 2 parts of the Srinagar city, that is in Kashmir, within a total distance of 5 kilometers. On the contrary, there is only one bridge over the river Jhelum at Ramban, that is in Jammu province, connecting the valley of Kashmir with the rest of the country. That may be true for most of the other big cities, states and countries of the world. In other words, with the big cities divided by rivers and streams, a bridge has to be placed where it is needed irrespective of the subsurface geology. In case of bridges, the design, the stability and durability depend to a great extent on the subsurface geological conditions that must be properly investigated and cautiously interpreted. In any major bridges construction project, the designer is keen to place the bridge abutments and piers on as sound and strong and stable rock foundation below as possible. This being so, the geological character that need to be investigated and thoroughly established, and that can be thoroughly established are the depth of the bedrock, the nature of the bedrock and the structural disposition of the rocks. Depth of the bedrock. In most cases, the river bed below the water is covered by varying thickness of unconsolidated natural deposits of sand, gravel and boulders. Such loose materials are not safe as foundations for bridge piers for at least two reasons. One is the piers placed directly on them would be unstable. The second one is the cover material is liable to be removed due to scoring by river water. As such, the piers must be placed on a stable foundation, preferably of rock under suitable thickness of cover material, so that it is safe from score by river water. The height of the pier from under the span to the foundation level therefore depends on the depth of the bedrock below the river water. Such sound bedrocks might be available within a depth of varying from 5 to 20 meters below the river bed, or they might not all be available even up to 100 meters or even more. All that depends on the local geology, which has to be investigated and understood. To achieve this, the drill holes are made all along the center line of the proposed bridges, even on the right or the left of it, till they reach this sound rock sequence or up to the reasonable depth or reasonable depth. Utmost care is needed not to mistake isolated big boulders buried underneath the river bed as the bedrocks. Boulders are rocks, but they are not bedrock and cannot be trusted as foundations for bridge piers. Nature of the bedrocks. The very first rock encountered below the bed cover material may not be suitable as a foundation. Three types of loads are to be borne by a bridge pier foundations. One is the compressive vertical load due to the weight of the bridge span and that of pier materials. The second, the horizontal loads due to the thrust of the water flowing above as transmitted directly and through the piers. The third, the dynamic complex load often inclined and sharing in character due to the heavy traffic on the bridges. Consequently, the bedrock selected as foundation for one pier must be strong enough to bear the sum total of these loads, not temporarily but throughout the proposed life of the bridges. The nature of the bedrock is commonly determined through a study of petrological characters and engineering properties, especially the strength values using the core samples obtained during drilling of test boreholes. A complete and very useful geological profile could be prepared all along the center line of the proposed bridge from the study of such core logs. These profiles would depict a complete sequence and even a structural disposition of the rock formations existing below the surface material of a design depth. A decision to place the pier on a particular depth is then a matter of judgment and design requirement. Most igneous and massive type of sedimentary and metamorphic rocks are quite strong, stable and durable as foundations for bridge piers and abutments. The group of weak rocks which might behave badly in the presence of water includes such types of as cavernous, limestones, chalk, friable sandstones, especially with clayey elements, and shale, clays, slates, schists and the layers of peat and compressible organic materials. Many of them are amenable to treatment by artificial methods. Structural disposition of the rocks. Ideally, the horizontal attitude and uniformly massive structures with the depth or desirable characters in the foundation rocks, as these offer a inherent resistance against failure. Inclined rocks in a confined situation under the bridge piers are considered quite safe if these possess a normal strength values. Folding and faulting might cause some uncertainty in establishing a perfect geological profile, but are not otherwise negative factors. Acute fracturing and profuse jointing is, however, undesirable at foundation level, as this might cause a settlement behind the allowable limits. When the bridge sites are located in the zones of seismic activity, the foundations are required to be designed for additional seismic loads as specified in the codes of respective areas. In the glaciated areas, special care must be taken to establish the existence of drowned or buried valleys that might be filled by secondary material of most heterogeneous characters. In such cases, a bedrock may be encountered only at great depth, and it may be desirable to reach it through a piers, etc. Occurrence of drowned valleys is considered one of the major complications in bridge foundations that limits the options of a design engineer. The factor of scoring must never be overlooked. Riverbed material and rocks under them at shallow depths are liable to removal by scoring. The score itself is a function of river velocity and direction of the currents on the one hand, and nature and degree of consolidation of the rocks on the other hand. Bridges are crucial transportation links that carry roads and rails traffic across the rivers, gorges and other roads. When a bridge collapses or closes for repairs, it can cause a massive traffic problems or strand people altogether as they live on an island. The bridges collapse are the result of multiple factors. For example, a flood that damages bridges piers might not have caused a collapse except for design flaw and poor maintenance. A train crash. This type of bridge collapse is extraordinarily rare, but one of the worst rail disasters in history, the Eschede train disaster, was a bridge collapse caused by train impact. In 1998, a high-speed train travelling through Germany suffered a mechanical malfunction of one of the wheels. The broken wheel struck a switch and shifted it, throwing subsequent cars onto a different track. Many bridges cross rivers and other bodies of water. Boats passing under a bridge are usually moving pretty slow compared to a train, but boats have incredible masses, and this means that even a barge, which typically creeps along at very slow speeds, can impart a tremendous force if it collides with bridge piles, and that force is sufficient to knock down the bridge in some cases. Floods cause bridge collapses in a few different ways. Severe floods can cause rivers and cracks and overflows, picking up debris like trees, cars and parts of the houses. When the river passes under a bridge, the high water level smashes the debris into the bridges. If the impact does not destroy the bridge immediately, the weight of the piled up combined with the force of the flowing water pushing on it and can bring the bridge down. This is what happened to the Conemaugh Viaduct in 1889 when the South Fork Dam in Pennsylvania collapsed, unleashing a massive torrent of water down the little Conemaugh River. A surprising number of bridges collapse as they are being built. Unfortunately, some of the deadliest bridges collapses in history have occurred during the bridge's constructions. While a functional bridge may only have few vehicles on it, when it collapses, it takes hundreds of workers to build a bridge, all of whom may be in dangerous position in case of collapses. At times, the simple failure of small piece of the bridge caused by entire collapses, sometimes the low grade or faulty materials were used, rendering the entire bridge too weak and it cannot withstand the loads. There are bridges whose collapses was inevitable before the bridge was ever built. The fault lies not with the construction of the bridge, but the design itself. The bridge is doomed to failure from the moment it was laid out on a blueprint. The poor maintenance is a difficult problem to diagnose in the wake of bridge collapses. Many bridge collapses could have been prevented with more stringent inspection and maintenance routines. Bridges are the media for passage of roadways, railways, footpaths, etc. Bridges, especially over major rivers, hilly and mountainous areas, are very important. It is necessary to gather techno-feasible informations about the regions. Regional geology influences the geological conditions of the regions. Hydrogeological studies of the regions exhibit the water table or physiometric conditions of the proposed area. Deep foundations for major bridges require subsurface details of the proposed area. Foundation type and design are important components in bridge constructions. Seismic zoning map of India reveals the seismic factors of each zone. Thank you.